Hello and welcome to this presentation. I am Sheila Mugala, a PhD student with the Department of Electrical and Computer Engineering at Makerere University in Kampala, Uganda, East Africa. The title of our work is Coverage and Rate Analysis of a UAV-enabled heterogeneous network. The internet usage in developing countries is still low. For instance, Africa has an internet penetration of 19% compared with a world average of 54%. This difference is attributed to the inadequate telecommunications infrastructure, especially in the rural areas, the high cost of connectivity, and other factors. The prevailing coronavirus pandemic has increased demand for telework, telemedicine, and other online services, which has further exacerbated the pressure on the existing infrastructure. We therefore need to seek new methods to enable affordable and universal ICT access that are also environmentally friendly, for instance, through lower power consumption. There is a global trend towards the use of aerial base stations, abbreviated as ABS, especially the unmanned aerial vehicle or UAV or drone base stations. They are used for capacity enhancement and provision of connectivity where the terrestrial infrastructure is non-existent. We identify two pertinent use cases for UAV BSs for developing countries. The first is that they can be deployed at emergency and temporary events, especially for disaster coverage. The second is that they can enhance capacity of the terrestrial network at hotspots. In this work, we analyze the integration of ABSs in a cellular network to identify key network parameters that affect communications performance and to reveal inherent trade-offs. We now briefly present use cases for UAV BSs. The figure shows a high-altitude platform UAV equipped with LTE equipment that is deployed by Google Loon at high altitudes, that is, 20 kilometers above the Earth's surface. Because of its high altitude, it can provide a large coverage area suitable for rural remote coverage. However, it is costly. Another use case involves a tethered UAV, also with LTE equipment. These have been deployed by AT&T in USA for disaster management. They use a cable for both communications and power transfer. Though suitable for emergencies, they have limited coverage because of the cable. A tethered helicite is shown in the figure. It is similar in performance and limitations to the previous case of a tethered UAV. Another use case involves the use of a drone in a wireless network. The drone is battery powered and is also suitable for emergency and temporary events. Its major challenge is the short operating time of 30 minutes. However, advancements in battery technology promise longer operating times. Another issue that arises is the possibility of collisions, but collision-aware mechanism is included in contemporary drones. These drone BSs are the focus of our work. Our research objectives. The main research objective is to develop an architecture for a UAV-enabled wireless communications network to enable analysis of key features and inherent trade-offs. Our specific objectives are as follows. 1. To analyze the coverage probability with network parameters including path loss exponent, UAV altitude, density, and bias. Secondly, to analyze the spectral efficiency for the network parameters in one. Thirdly, to reveal inherent trade-offs of a UAV-enabled heterogeneous network. We next present our methodology. We considered a three-tier heterogeneous network as shown in the figure. The first tier consists of UAV BSs, the second tier consists of macro BSs, and the third of small BSs. In the figure, we show the height of the antenna, labeled H, and the ground distance between the antenna and a user located at the origin, marked O. We distinguish between line of sight, LOS, and the non-line of sight, NLOS links. We assume that BSCs in the same tier use the same transmit power. Another assumption is that all BSCs use the same frequency, that is, universal frequency reuse. The implication is that every BS except the serving BS is a source of interference to the user. Our BSCs, referred to as nodes, are placed in the network using two-dimensional homogeneous Poisson point process. The figure shows a snapshot of the nodes in the network as placed by the Poisson point process and their coverage areas marked by the blue lines. The red stars represent the drawn BS, the black rectangle for the MBS, the blue circle for the SBS. The propagation channel where the signals travel is an important parameter for wireless channel modeling. For the large-scale propagation, we define the path loss in equation 1. Path loss simply tells us how fast the signal degrades with distance between a user and a base station. For the small-scale fading, we adopted the relay channel, which is the simplest but also models the worst-case scenario with no line of sight. We next define the communications performance metrics that we used in this work. They are very relevant and widely used in the analysis of cellular networks. The first is the coverage probability, which is the probability that the signal to interference plus noise ratio, or SINA, is above a given threshold tau. A user is connected to a BS if the SINA is greater than the threshold. Otherwise, it is not connected. The second metric is the spectral efficiency of the network. We use the average rate per user, which has units of bits per second per hertz. Next are our results. We used Monte Carlo simulations with 10,000 runs in MATLAB. The table shows the simulation parameters which we used, including the power of the tires, the bias factor, the excess path loss, densities, altitude, and environment. We considered an urban environment with ITU parameters as shown in the table. Our first result gives us the variation of coverage probability with SINA threshold and path loss exponent denoted alpha as shown in the figure. We observe that the coverage probability of the network reduces as the SINA threshold increases. This is expected since the requirements at the user, that is received SINA, increase with SINA threshold. When we look at 0 dB SINA and compare the coverage probability for a path loss exponent of 2.5, which represents lowest path loss or signal degradation, and path loss exponent of 4, which represents the highest signal degradation, we observe that coverage probability increases with path loss exponent. We assert that for higher path loss exponent, signals from interferers are degraded more. Therefore, this results into an increase in the SINA and hence the coverage probability. The next result shows the per-tier coverage probability. We observe that the coverage probability of the drawn BSs marked with blue crosses is almost coincident with the total coverage probability, which implies that drawn BSs provide most of the network coverage. This is expected since they experience less signal degradation due to path loss or distance and therefore offer more favorable propagation conditions. We are interested in establishing how the coverage probability is affected by UAV altitude. It decreases with UAV altitude because at higher altitudes the path loss is greater. The figure shows that average rate per user also reduces with UAV altitude because of increasing path loss. The UAV density is the number of UAVs deployed per meter squared. From the figure, we can see that as UAV density or the number of UAVs in the network increases, the interference increases, which results into a lower average rate per user. From our simulations, we saw that bias has minimal effect on both the coverage probability and the average rate per user. The potential beneficiaries of UAV or drone BS technology are network operators for improving capacity at hotspots. Governments can deploy drone BSs to provide e-government services, especially in rural, remote areas of developing countries. They can be deployed quickly to assist disaster or relief efforts. Telecommunications regulators and civil aviation authorities can refer to our results as they set regulatory limits on critical parameters such as operating altitude, speed, and number. Manufacturers can also use our results to cautiously select suitable materials that can withstand the environment. In conclusion, a network with aerial BSs gives good coverage of about 99%, moreover with most of it provided by the aerial BS. We have looked at key network parameters, that is, UAV altitude, density, and path loss exponent, and their effect on the communication performance. Going forward, we need to develop an analytical framework to define the coverage probability and also experimental work to complement our work. Thank you for listening and thank you IST Africa for organizing this conference.